Assalamu alaikum. I welcome you all to another tutorial on power electronics. In today's class, we will see how we can have multiple outputs from a single switch mode power supply. Number one. Number two, how we can provide isolation between the input and the output. And for that, we will start the topic of the isolated converters. Isolated DC to DC converters provide us two advantages. First of all, let us write them, and thereafter we will start with the very first topology. The first advantage is that the ground is electrically isolated. That is, input and output are isolated, and this is not the case for the converters that we have studied. In all the converters that we have studied, whether it was the buck converter, the boost converter, or a buck boost converter, input and output were having the common return paths. However, there are some issues that forces us not to do so, specifically when it comes to the EMI problems, and therefore we require to have some isolation mechanism between the input and the output. One way of providing this isolation is to use the transformers. Now, there are two possibilities for a transformer. We can either use a transformer on the AC side. For instance, if we have an AC supply and we will rectify it for making it a DC, and then we have this DC to DC converter, and then we have this DC to DC converter, and here we have the load available. For instance, we have this particular system. We can provide an electrical isolation by providing a transformer here, right? Now, if we provide a transformer here, then this transformer has to be designed on this system frequency F, which is usually between 60 Hertz and this 50 Hertz. Now, with this 50 and 60 Hertz system, the transformer core requirement is high, and therefore it will not only add the weight and the size in the system, it will also increase the price of the system. So this is not an economical solution to use in a transformer which is operating at the line frequency of 50 or 60 Hertz. What we can do is we can make a transformer part of the DC converters, right? So we will integrate the transformer as an integral part of the DC to DC converter. What is the advantage here? That these converters are usually operated way above the audible frequency range. So for instance, for a 30 kilohertz transformer, the requirement for the size, the weight, and the core, and the price, they become significantly reduced because of the increased frequency of the converter. So electrically isolation means we make transformer part of the converter, and this reduces the size and the weight required for isolation. This is the first advantage of making a converter based on the transformers. The second advantage here is that the multiple outputs, multiple secondaries, or multiple outputs are possible, which was not possible for the basic converter circuits that we have studied. For here, because we have multiple outputs available, we can have a transformer which has only one primary. We have the two secondaries available, and these two secondaries operate with their own circuits, and we can have multiple outputs through these transformers which are embedded into the converter circuit. So with that, let us start with the first and the most basic type of a converter, which is known as a flyback converter. Now, before we begin with this flyback converter, let us have some assumptions. So the first assumption is that the circuit operates in a in a steady state condition, which means that we will neglect the transients that appear because of the switching of the switches in this particular converter. The second thing here is all components are ideal except for a transformer, because for the transformer we will try to model the transformer in terms of the magnetizing inductance, and we will see what is the advantage of considering that magnetizing inductance in the understanding of the whole system. The third thing here is that the switch that will use here will be assumed on during D time T and off during 1 minus D into T, which means that the concept of duty cycle that we studied in the basic converters, it will stay intact. So for when we will turn on the switch, it is supposed that the switch shall have the duty cycle D applied, and when it is off, it is the rest of the switching time at which the switch will remain turned off. Number 4 is output voltage ripple is considered negligible, which means that the output capacitor is large enough that there is no ripple across the load. Let us first of all study the transformer model before we begin into this flyback converter. Now we know that if we have this transformer, and here we apply the voltage V1 and the current I1 flows through this winding, and here we have this winding V2 and 2 such that we have the current flowing out of this particular winding. We can model this using this symbol, where we have this one as V1, this is I1, this is I2, and this is this. We also know that there is a dot polarity where it exists in a transformer. So supposedly if this is the dot polarity here, this indicates that the current that I1 enters the dot terminal such that I2 leaves the dot terminal, and I2 is related to this winding N2, right? Also V1 has positive terminal with the dot end, and V2 also has a positive terminal with the dot end. Now if this thing exists, then we do know that V1 over V2 is equal to N1 over N2, and we also know that I2 over I1 is equal to N1 over N2, such that this whole states that the input power in a transformer is equal to the output power, provided that the system has no losses. Now if I want to model this one, if I want to model this particular transformer, there are some things that we need to add. The first thing is the resistance and the inductance of the primary winding, which are the leakage inductances of the windings. So let me model them such that we have this one R1, this is L1, this is R2, this is L2, this is N1, this is N2. Here we have the system available, and also we have the RM and we have the LM here, and this RM and LM can either be designed refer to the primary or refer to the secondary. Here we have this voltage V2 available, right? This is I2, this is I1. Again we have the dots here. This is, let me write this one as I1 V1 and this one is the I. And this, in this particular, if you see this particular model of a transformer, we notice few things, that this Rm represents the core losses, this Lm represents the magnetizing inductance, R1 L1 and R2 L2 represents the losses that are encountered in the primary and the secondary windings respectively. Now practically we require to have some detailed model of the transformer, but not this much detailed so that we can have our analysis in a very hassle-free manner. So one compromise solution is that we omit most of the things from this particular transformer model circuit, that we will neglect these model components except that of an Lm, right. This means that for an ideally we have R1 L1 R2 L2 equals to 0, while we have this Rm is infinite, right, while we have this Rm equal to infinite. So only thing what we are left here is this transformer winding alongside this magnetizing inductance Lm. This magnetizing inductance Lm is very important in understanding the basics of isolated converters. And likewise, a normal inductance, we can apply all the rules of an inductor on this Lm, such that the volt second product across this across this magnetizing inductance Lm should also be satisfied if the circuit is operating in a steady state condition. So with this in mind, we will use this transformer model for all isolated converters, right. So let us draw the diagram of the flyback converter. We have already assumed few things for the flyback converter. We have a switch here. This is connected with this supply Vs. We also have a load here. This is R, this is C, this is D. Let us say this is SW, which is the switch. This is Vs. So the first thing here is that we need to model this transformer using the model that we have discussed just earlier. For that, I will draw the magnetizing inductance Lm here. I also need to define the polarities here. This is the polarity. Notice that this N1 and N2 have polarities in these particular points. This is very important to understand the operation of this particular converter. We also see that the current through this winding is I1, this is ILM, this is VSW, this is VD, here we have this IC, here we have this I0, this is V0, and here we have this V2 available here. Now we will analyze this circuit just like we have analyzed the isolated non-isolated converters. This switch can be turned on and off at a very high speed. Thus this DC circuit Vs is actually chopped at a very high frequency, enabling it to be used with this particular transformer, right? Otherwise transformers cannot be used with the solid DC system. It will saturate the core, and therefore thereafter the transformer will not work. So in order to reduce or in order to make it happen, we chop this DC at a very high frequency, such that we have actually a chopped DC waveform appearing across the primary side of this particular transformer. Now, one important point here is that because this switch comes in series with this primary winding, why cannot we use this switch on somewhere here? It is because, let me write it here, the switch SW, which is usually a MOSFET, is used on the low side to provide ease in the gate driver circuitry, right? So a low side driver is usually considered easy, and it is actually easy compared to a switch which is connected on the high side, or which is known as the high side switch, because for that you require to have the boot driver circuits, and that adds the complication and complexity in the system. So we only require to have a gate driver circuitry easy, and therefore this switch is connected on the bottom side or on the ground side of this particular converter. So for that, the switch can have two states, one when the switch is on and the other side when the switch is off. So let us analyze this particular circuit using the switch on and switch off conditions. So here we have let us say when the switch is on. When the switch is on, we have this is our input. Now, when we turn on this particular switch, you can notice here that this dot end becomes positive, and therefore this dot end also becomes positive, which means that we have this non-dot end negative, and because the diode has an anode connected with this non-dot end, therefore diode will become reverse biased, and therefore I1 and I2, which is this one, which is this current I2, they both become equal to 0. Consequently, what happened here is that all the current which is flowing through this source IS actually flows through the magnetizing inductance of this particular transformer IL, and therefore this V1, which is this voltage V1, it becomes equal to Vs, and that becomes equal to Lm into DILm over dt, or the voltage across this particular magnetizing inductance Lm. So VL is equal to Lm DILm over dt, and this provides us the rate of change of the magnetizing inductance current, that is equal to Vs over Vf over L, right. Now, if you notice here, likewise all the converters that we have studied before, this ILM net change in this particular current, it will start from some value. It will start from some initial value, and it will end some final value. So during the time when it is turned on, it will start from that initial value and it will end to that particular value. Therefore, we can say that the net change in this ILM when the switch is closed is equal to Vs over Lm into dt, because dt is the time during which the switch was off, and this ILM started to increase linearly at a rate equal to Vs over Lm. On the secondary side, we have this is plus minus, this is V2, and this V2 is actually equal to the V1 times the turn ratio of this particular circuit, and therefore this one is equal to V1 over N1 over N2, right, and V1 is equal to Vs during this switch on time, and therefore that is equal to Vs into N1 over N2, and that is the voltage across the secondary winding of this particular converter. I am not talking about the output voltage because it is equal to V naught. Therefore, the voltage which is blocked by this particular diode, this is plus minus this Vd, this voltage which is blocked by this particular diode Vd is equal to minus V naught minus Vs into N1 over N2, and that because it is less than 0, so this indicates that the diode is in a turn off state or it is in a reverse bias mode. Now this particular concept, you can see here that we have seen that this diode is now is turned off, therefore this I2 is equal to 0. So I2 is equal to 0. What does this mean? Because this I2 is equal to 0, this means that the transformer primary current is also equal to 0, owing to the relation that we have studied earlier, that I2 over I1 is equal to N1 over N2. Here we have this I2 equal to 0, which means that this I1 is also equal to 0, and all the current flows through this magnetizing inductance Lm. Practically this means that we have a transformer where the current in the primary winding increases linearly while we have no current coming out of the winding of the flyback transformer. So what happens when we have this switch off? Let us say we have the switch off. Now when we have the switch off, we have here we have the switch off, and we have this is the circuit. Notice these two polarities. This is Lm, this is ILM, this is V. We switch here. This is plus minus V naught, this is plus minus, this is V2. Now what happened here is, if you see here that this Lm is actually an inductance. We have said that all the rules of inductance applies on this magnetizing inductance Lm. With this thing in mind, the current through this Lm cannot be equal to 0 instantaneously. That it will revert, it will, in order to go in the same direction, it will circulate through this winding N1. When the current enters through this non-dotted end into this N1 and leaves this non-dotted end, this means that the current enters into the dotted end of the other winding N2, means that now this particular point is now positive, and therefore this is also positive. So this diode D2 becomes on, so D2 becomes forward biased, and therefore we have this I2 flow out of the winding of this secondary side of this transformer N2. So for this particular operation, this V2 becomes equal to, because now this diode is on, so V2 becomes equal to minus V naught, because this is the positive end and here we have the positive terminal on the top side of the secondary. So V2 becomes equal to minus V naught, and this voltage V2 actually comes on the V1 as well because of the transformer operation. So it is reflected back from the secondary side to the primary side, and that has an impact on the overall rating of the switch that we select for the operation of a flyback converter. So we have this V1, but let us say what is V1. Here we have V1 equals to minus V naught into N1 over N2. This is the turn ratio here. And also we have V2 equals to minus V naught. And now if we see about this rate of change of the current through this Lm, then we have voltage Lm dilm over dt, which is the voltage across this, which is the voltage here across this magnetizing inductance Lm, that is equal to minus V naught into N1 over N2, and therefore I can say that the rate of change of current is equal to minus V naught over Lm into N1 over N2, and this negative sign shows that the current will now have a decreasing slope during the time when the switch is now in a turn off state. Also we should be required to have this delta ILM, which is now open, so it will start from that final value and it will come to that initial value which was the start of the previous system when we have the switch on. So during this particular time when this delta ILM is open, then we have minus V naught over Lm N1 over N2 into 1 minus D into T, because this is the time during which the switch is turned on. Now to find out the transfer function, we will use this equation and this equation, right. So since in a steady state circuit or in a steady state mode, the net change in the inductor current is 0, therefore delta ILM and the delta ILM open must be equal to 0, right, because the steady state condition exists and therefore there should be no net change in the inductor current. It starts from that initial value at the start of the switching cycle and it ends at that particular value when the switching cycle ends. So if I add these two together, Vs dt over Lm minus V naught 1 minus dt over Lm into N1 over N2, that is equal to 0, and this gives me V naught over Vs is equal to d over 1 minus d into N1 over N2. Now if you notice here, this particular expression till this one, this is nothing but a buck boost converter, base transfer function, and this is actually a new term which is added here. So what we can say is that a flyback transformer is actually an improvised version of a buck boost converter. It provides us the same transfer function compared to that of a buck boost converter, except there are two things. The first thing, it is not inverting, it is actually a non-inverting type of a system. Second thing here is that we have an additional control on the output through this fixed transformer turn ratio, that is equal to N1 over N2. Let us find out the peak currents that are required for this particular transformer, but before that let me draw the waveforms here. So here we have this ILM which starts from this initial value and it ends somewhere here. This is the peak value. Here we have the delta ILM. This is DTS, and from here we have the 1 minus D into DS, right. Also we have, for this particular converter, when the switch is on, this is the current through the switch SW, and it only flows when we have the switch on. This is DTS. This is also equal to the source current IS. Similarly, we have this type of a current that flows through the diode ID. So this is the diode current ID. The capacitor has this type of a current shape as evident from the analysis. This is IC, and here we have this is equal to minus V naught over R, and the last one is the voltage, that is equal to Vs. It is the voltage across the primary. This is V1, this is Vs, and it is equal to minus V naught into N1 over N2, which is the transformer voltage reflected from the secondary side to the primary side when we turn off the switch. So this is the voltage across the primary winding V1. Now Now, based on this particular thing, let us have a look on the switch stresses that are imposed on this particular converter. Here we have this peak current ID that is equal to minus I1 into N1 over N2, and that is equal to ILM into N1 over N2. So this is an additional term we need to have a look on this turn ratio N1 over N2. Also we have VSW, that is equal to Vs minus V1, that is equal to Vs plus V0 into N1 over N2, which means that this switch, compared to a buck boost converter, it has to also take care of this reflected voltage due to this turn ratio N1 over N2. So this is equal to N1 over N2. So now if we say if this N1 is equal to N2, N1 ratio N2 is equal to 1, for example, we say that this turn ratio N1 over N2 is equal to 1, and we also say that the output voltage is equal to the input voltage, then this V switch is equal to 2 times the Vs, right? So it has to be able to block the twice the voltage of the input applied voltage, and therefore the switch voltage rating are higher than that of the conventional converter that we have studied. Also, you should notice here that this IC is equal to ID minus IR, that is equal to ILM into N1 over N2. This is the diode current minus V0 over R, and this is evident from this particular waveform. Also, you should note here that this, because the transformer is assumed to be ideal, therefore the supplied voltage is equal to the output voltage, and this is equal to VSIS is equal to V0 square over R. What is this IS? This IS is the source voltage, is the source current which only flows when we turn on the switch S1. Otherwise, there is no source current that flows through this particular circuit, and therefore this is equal to Vs into ILM into D, because this ILMD is the time during which the source current actually flows, and that is equal to V0 square over R. So ILM is equal to V0 square over Vs R into D. This is the magnetizing inductance current, right? Using the input output voltage relation, we can write that ILM is equal to Vs D over 1 minus D square into R into N2 over N1 whole square, and that is equal to V0 over 1 minus D into R into N2 over N1. Now we need to also specify the maximum and the minimum values of the current ILM, so that we can establish what is the boundary condition mode for this particular DC to DC converter. So ILM max comes out if we add up the peak current component into it. So this is delta ILM. So if this is the ILM, then we need to just add this half of delta ILM here, provided that we have a symmetry in this magnetizing current component. So that becomes equal to Vsd over 1 minus D square into R into N2 over N1 whole square plus Vsdt over 2Lm, and similarly we can find out this minimum component by having the delta ILM minus 2. This is the only difference. So this plus becomes equal to minus 2. We have earlier discussed in the previous classes that this IL maximum provides you information about the peak current rating of the devices, while the IL minimum defines you the minimum value of the inductance that ensures the continuous conduction mode. So if this IL minimum is 0 at the boundary of continuous conduction mode and the discontinuous conduction mode. So through this we can find the LM minimum to ensure a CCM mode, right? And this can be calculated by putting this IL minimum equal to 0. Now, if I put this IL minimum equal to 0, then we have this V as D into 1 minus D square R N2 over N1 whole square, that is equal to V as dt over 2 L M, and this is the minimum value, right. So, from this particular expression we can find out the Lm minimum as equals to 1 minus D square into R divided by 2F, and this comes equal to N1 over N2 whole square. So, this is the minimum value of the inductance which is required to ensure that this particular converter operates in a continuous conduction mode, right. So, we always want to have a threshold or a factor of safety involved, and therefore, whatever is the minimum value, you have to add some 25% or 10%, 15%, 20%, depending on your loading requirement. You can also always have a factor of safety involved before selecting the minimum value of the inductance to ensure that the converter always stays in a continuous conduction mode. Now, other than that, we can actually establish the value of Lm using the expression that the delta ILM is equal to Vs dt over Lm, right. This is the net change in the whole current, and therefore, this Lm is equal to Vsd over delta ILM into the switching frequency f, right. For a flyback converter, the output stage is similar to that of a buck boost. Therefore, the expression for capacitor remains the same, and that can be used for a flyback converter output capacitor field as well, and that is equal to delta V naught over V naught is equal to D over RCF, and this is through which we can find out the capacitor C naught here, right. So, that's all for today. In the next class, we will discuss the second kind of an isolated converter, which is known as a forward converter. I hope you have enjoyed the lecture. Thank you very much and take care. Allah Hafiz.